Thank you, Mr. Chairman. So, this is the outline of my talk. First, I will start with motivations, then I will describe both the refined or micro and coarse or macro models. Then I will apply a typical perturbation method called multiple scale method. I will discuss some numerical results, and eventually I will draw up some conclusions. So let's start with the motivations. We want to study the dynamics of two linked multi-story buildings under the effect of wind which is blowing orthogonally to the plane of the structure. And to do so, we want to introduce an appropriate model in order to easily evaluate the aerodynamic forces. At the end of the story, we will get to a 2 degrees of freedom nonlinear dynamical system where the wind, which is assumed as turbulent, will provide three simultaneous sources of excitation. In particular, the steady part, the stationary part of the wind will provide self-excitation, while the turbulent part will give both external and parametric excitations. So in this case we want to study what happens to galloping, and in particular which is the interaction between the 2 degrees of freedom. So this is the refined model. It is constituted by two multi-story share-type towers. This is the front view. This is the top view. As you can see, they are linked at the tip, and the wind is blowing orthogonally to the. Thank you. Yeah, thank you. The wind is blowing orthogonally to the plane of the structure, as you can see here from the top view. And we apply the nonlinear viscous linear device here, and we want to study the dynamics in the plane of the structure. It means that we are considering just the lift force and neglect what happens in along wind. To do so, we introduce a coarse model, which is constituted by two shear beams. It means that we are considering axis lines here, which are flexible, and rigid cross sections, which are able just to displace and not to rotate. Here, V1 and V2 are the two displacements of the axis lines, and in such a way, the kinematics is described by these equations. In particular, the unique not vanishing strain measure is the shear 1, which is here for each tower, of course, while the curvature is identically vanishing. If we consider among the balance forces the one for the shear force, it is written here, where Pi are the external forces constituted by the aerodynamic terms and, of course, inertia and external damping. We introduce a viscoelastic law for the unique active variable, stress variable, which is the shear, in a Kelvin-Voigt model. So you can see here the shear elastic stiffness, and here the term due to the internal damping. So what we want to do now is to evaluate, to identify the value of this constant here. And to do so, we apply an identification through comparison of the elastic potential energy between the refined and coarse models. So we obtain this expression for the shear stiffness, in particular depending on the number of columns for each story, the bending stiffness of each columns, and the inter-8 story. 8. So the equations of motions are these two partial differential equations in terms of displacement of the axis lines with boundary conditions here. This one is at the tip where we have the nonlinear viscous device, which is one of the two sources of nonlinearity. One is this. The other one is in the aerodynamic forces, which are evaluated under the quasi-steady theory. You can see here the expression. I will skip details, but I will say that these terms are aerodynamic coefficients, and U, appearing here as a square, is the wind velocity, which we decompose as a steady part plus a time-dependent part due to the turbulence, assumed as multi-frequency. So now we apply a Galloping projection on the first mode of each tower in order to get two ordinary differential equations, which are nonlinear of course, on the dependent variables, which are the model displacements x and y. And we put the system in a one-to-one internal resonance. It means that the towers have the same, more or less the same natural frequency. As you can see here, the wind will produce three sources of excitation. In particular, the steady part, which is the blue term here, will give self-excitation. When the steady wind reaches a critical value, the linear damping vanishes. In particular, when the wind overtakes this value, the linear damping will be negative. On the other hand, the turbulent component will provide both parametric in red and external excitations. We consider the turbulence in this form with two frequencies, and moreover we use as a critical value for this frequency 1. It means that in this case the external excitation will be 1-to-1 resonant, and the parametric excitation 1-to-2 resonant. It means it's the worst situation here. Now we can apply the multiple scales method, and we introduce the sliding parameters. In particular, you can see here sliding with respect to the critical value of each parameters. You can see here the steady wind sliding, here the tuning, the internal detuning, the damping ratio, and here the external detuning. We apply the multiple scales technique. Here there is the series expansion. We introduce two time scales, the fast one and the slow one. So we obtain the perturbation equations. At the first order, we have the generating solution, which is, as you can see, harmonic with amplitudes, which are complex amplitude, which are unknown at this level, depending on the slow time scale. At the second order, we have corrections due to the nonlinear terms, as well as damping and forces. And so here we can apply the solvability condition. It means that we neglect the secular producing terms in order to obtain the amplitude modulation equations here, which are differential equations in the complex variables A1 and A2. And these equations in particular are the normal form for the one-to-one internal resonance double hop bifurcation with some perturbation terms due to the turbulence here, the green and the red terms. So we can go to the real equations, which are four here, introducing a polar transformation. In particular, A1 and A2 are the two real amplitudes of oscillations of the two towers, while phi1 and phi2 are the phase differences. So we can consider the solution here of the problem. We can study the solution, for example, just when we apply self-excitation. It means that we drop out the turbulence here. And we can see the stability diagram for the trivial solution in terms of the steady part of the wind velocity and the tuning, damping ratio here. And in this region we have stability of the trivial solution Here we have two limits, which are pitch for bifurcation limits, and here the solution is unstable. And these boundaries are independent of the internal detuning parameter. If you can see here, the planes are not changing in terms of sigma. But if we follow a path here, for example this one, and we see what happens in the post-critical, in terms of post-critical behavior, we can see a strong dependence on the internal detuning. The bifurcation points remain in the same place, but the post-critical behavior in terms of steady solution changes when we change the internal detuning. In particular, when we are in perfect resonance internal resonance conditions, both the amplitude are involved. It means that the two towers oscillates with periodic time law with the same frequency. If we increase the internal detuning, we get to a situation where one tower stops to oscillate, or it's better to say it oscillates at higher order, while the second tower oscillates at these amplitudes, which is the typical behavior we found in another work in case of non-resonance double-up bifurcations. It is an important results. It means that, of course, it happens both if we increase or decrease internal detuning. It means that although there is an ordering violation, the equations describing the internal double-up bifurcation continuously can describe the case of non-resonant double-up bifurcation. If we introduce also parametric excitation, you can see here again the stability diagram for the trivial solution, and the pitchfork bifurcations here split, and we have a lower critical condition for this type of bifurcation. Here we have on the other hand, a Hopf bifurcation diagram, and if we follow up a path here, for example, in this way, you can see the steady solution here, which closes at two bifurcation points, and moreover you can see periodic solutions in terms of the amplitudes. It means that here the towers are oscillating in a quasi-periodic fashion. What happens if we introduce we change the external detuning? In perfect resonance condition, we have the typical crossing phenomenon between these two boundary limits, these two stability limits of the trivial solution. When we apply a perturbation here, we have the classical avoiding of the surfaces, but if we draw a path here, we can see a post-critical behavior which is not qualitatively different from the previous case. If we apply the three, in a simultaneous way, the three sources of excitation, we lose the trivial solution. Okay, and we can see that we have in this case, for example, periodic oscillations of the two towers with amplitudes which are larger than the previous case where we have only self and parametric excitation, which is shown here in dotted lines. Moreover, we can see also quasi-periodic oscillations, which are in this case unstable, but of course there are also some stable results. Okay, so to draw some conclusions, we have considered an homogeneous model to simulate dynamics of a tower system under the effect of the wind. So we consider shear beams. We obtain a 2 degrees of freedom system after a Galloping projection, and consider the concurrent occurrence of self-parametric and external excitations. When we consider just the self-excitation, we are in galloping phenomenon, in particular resonant double-hop bifurcation in one-to-one resonant double-hop bifurcation, and we have seen that the equations of motion, the normal form, continuously describe also the non-resonant case. When we consider external and parametric excitations, we have perturbation of the bifurcations with possible reduction of the critical conditions. Thank you for your attention.
What happens, I don't know if it's even conceivable, if beams can bend?
Okay.
Assume that there is only
it was because we consider in a refined model share type frames, of course. So I think that it is the better way to build an homogeneous model describing share type frames. Of course, if we consider not share type frames, we can consider. I think it is the following presentation, but I think that you can consider richer models in the course. I think it will be the same. Okay, not very different.
You had two towers.
Yeah.
And the wind came from.
Yeah.
And they move like that.
Yeah. It's the lift force. Okay.
Explain.
Yeah, it's a typical aerodynamic condition. Okay, the along wind effect is often negligible. Okay, so what happens in the direction of the wind? When you apply wind, also stationary wind, to a section which is section which is not circular, you have also beside the along wind force, you have also a crosswind force which is called lift. Okay, and in this case, if we have the two towers, the lift force let the towers move in the plane of the structure. It's a typical aerodynamic phenomenon. Okay, that you can see in the nature.
What is the sensitivity of the response to the damping that you introduced in the
damping is important. I mean, we have considered in particular damping, which is typical for this kind of structures, okay? But as you can see, we have considered also damping as a bifurcation parameter. So we modified the damping. We have seen what happens if we modified damping, and it's important because it can move from, for example, pitch for bifurcation to hop bifurcation. It means that if you change damping, you can have periodic oscillations of the towers or quasi-periodic oscillations of the towers. So it's an important parameter, of course.
Thank you very much.
Thank you.